aka fucking stupid retard. What up, guys? It's your boy FazmitFan1994, aka Young Galois, aka Kwanucha. Today we're gonna be solving this bad boy right here. I came up with this ODE a couple days ago. Thought it looked interesting. Yeah, this is like my second take of this shit. So yeah, let's begin anyway. So to get our general solution y, we know that we can just apply the superposition principle such that our general solution y is going to equal to the complementary solution or the homogeneous solution y sub h and the particular solution y sub p. Since here this equation is not homogeneous, we have this little term over here, so we're going to need this as well as this. So we're going to solve the homogeneous case first. So let's see, so we got x cubed y triple prime h x squared y double prime h plus x y prime h minus h equals to 0. Okay, so this is what we have to solve first before anything else. Cool, okay, so this is what we have to solve first. And if you know a little bit about ODEs, you might notice that this is actually what's known as a Cauchy-Euler equation. Because as you can see, the power on this x here on this variable is the same as the order of the derivative. So you get 3 and 3, 2 and 2, 1 and 1, and 0 and 0. Yeah, so there's actually going to be some standard techniques that we're going to have to use. It might get a little confusing, but if you know, I don't know, calculus, basic calculus, you'll be able to keep up. So one way of doing this is to actually just we're gonna, solve for using a trial solution. So we can let y equal to x to the lambda, some lambda. Lambda can be complex, such that lambda is an element of complex numbers. But that method is for pussies, so we're not going to be doing that. Instead, we're going to do something different. It's quite similar. We're not actually going to be doing reduction of orders on this thing. So instead, we're going to introduce a different substitution, or a more intuitive parameterization. We're going to let this variable coefficient, x, we're going to let that equal to the exponential function, e to the t. Which always works out nicely, because this is similar to the way we would solve an ODE with a linear ODE with constant coefficients. Except there it would be e to the lambda t, but you'll see later, it all makes sense in the end. So, which would mean that t is equal to ln of x. It's so fucking hot, I swear. It's like 40 degrees outside. I'm here doing this, goddamn. Anyway, so this is our t, right? Logically. So now we're gonna have to substitute this y of x with something. These y. So we have this function y h, this depending on x. Now we want to let that, so let this y h x equal to, now we're gonna have it equal to some different function, quite arbitrary, like phi, for example. Because, I mean, some people just say it's equal to phi of t, but that's pretty stupid. So instead, just phi of t, this new variable that we have here. But what's t? Well, t is just, so we're gonna get phi of ln x. Yep. So yeah, that's what we get. So, and we're gonna use this fact later when we're substituting back. But first of all, let's focus on this phi of t, and let's substitute it into this this equation to perhaps transform it to, I can't speak. To transform this ODE from one with variable coefficients to an ODE that has constant coefficients, because then it just becomes infinitely easier to solve. So we're gonna now differentiate y with respect to x, so y prime So this is with respect to x. And this is also with respect to x logically. So we can do this and we obtain that. The derivative of phi of t is phi prime of t, but since t is a function of x, we can't just leave it like this. So we have to differentiate t with respect to x. Fortunately, we know what t is. T is ln of x. So we're just going to multiply by the derivative of ln of x, which is 1 over x. I mean, it's also equal to e to the minus t phi prime of t, but it doesn't really matter. Like, at the end of the day, we're actually just going to be better off expressing this in terms of x. You'll see why later, because of these bad boys. But shh. Anyway, then we got our phi double prime of x, right? And now, because this is a product of two functions, we're going to have to use the product rule. So first, we're going to differentiate the 1 over x. So you know what this is, you should know this. Minus 1 over x squared, phi prime of t. Okay, the second term. So we're going to leave that alone. And now we're going to differentiate phi prime of t with respect to x. So we get phi double prime of t. But again, phi prime is still a function of t. So we're actually, or you know, it's a function of t, but t is a function of x. So if we're differentiating with respect to x, then we have to differentiate t once again, and that's still 1 over x, so we can just multiply it by that and we get 1 over x squared. So that's cool, we can just factor out the 1 over x squared to get phi double prime t minus phi prime. Okay, that's our second derivative. And lastly, because this is a third order differential equation, we're going to need the phi triple prime as well. So phi triple prime of x is equal to, yeah, I'm going to use this. We're going to differentiate these two terms separately using the product rule each time. So let's see. So here I'm just going to, well, again, you should know this. So that's going to be 2 over x cubed positive phi prime of t. Now, we're going to leave this alone. Differentiating phi, again, we've already done this, phi double prime of t, but once again, differentiating t, so we get minus 1 over x cubed phi of double prime of t. Is it phi or phi? Potato, potato, tomato, tomato. Who cares? Alright, so now differentiating this, that's going to be negative 2 over x cubed phi double prime of t. Now we're gonna, I'm running out of space. We're gonna leave that alone. We already know it's gonna be x cubed because we're just gonna differentiate with respect to t again. Phi triple prime of t. Alright, so I mean here we can just factor out the 1 over x cubed to get, we can put the higher order term first. Phi triple prime of t minus phi double prime of t minus phi double prime of t minus, goddamn, I'm done, plus 2 phi prime of t. Cool. Alright, cool. So this is our third derivative. Now, we're gonna collect these on one side and we're gonna have to substitute here, so let's do it. Okay, alright. So I've collected the derivatives there, and let's begin substituting. Sorry, I'm so out of breath. I'm actually just decaying in this room. Anyway, x cubed. So, well, notice, just before I do anything, if we substitute this, the x cubed and the 1 over x cubed are going to cancel out. Similarly, same thing when you substitute y double prime into this thing. The x squared and x squared are going to cancel out, and same thing here. So, we don't even need to have that there. So, they're just going to cancel out, as you can see. Like, if you need the visual representation of these canceling out. Yeah, wow. Incredible insight. Anyway, right. So all in all, we just get phi triple prime. I'm just gonna omit the of t for sake of brevity because really cannot be fucked. Minus 3 phi double prime plus 2 phi prime. Now minus, so these are actually gonna, this is gonna cancel out, but these are gonna get switched. So we get plus phi prime minus phi double prime. Cool. And now, lastly, plus the x is gonna cancel out, phi prime, and minus y. But what's y? 5t. Y. All equal to 0. Alright. And then we can just quickly collect all the like terms. So we get minus 4 phi double prime plus 4 phi prime minus phi is equal to 0. Alright! Amazing, awesome, cool, epic and relatable. We've transformed this ODE, this disgusting ODE with variable coefficients, into a nice ODE with constant coefficients, which is just so much better to solve. And I mean, again, you should already know this. I mean, I'm not gonna demonstrate the most rigorous way why I'm gonna use this parameterization, but again, it's gonna be very similar to this. But just intuitively, you can see that if all of these add up to 0, then phi and its derivatives must only differ from each other by some fixed constant, right? And I think we know a function that behaves like that, where its derivative is just some fixed multiple of the function itself, or of the other derivatives. Namely, we can let phi now, right? We didn't say what phi was here, but we now let it be e to the lambda t, because it's still a function of t. And now, that's cool. We have the generalized exponential function, where again we allow lambda to be complex, because otherwise it wouldn't be fun. Because since we're solving a cubic, we're gonna have 3 roots to open that complex. We'll see anyway. I'm just gonna rub this down. We don't need that. We don't need these either. Alright, so phi prime is then gonna be lambda e to the lambda t. Some people use r, but like I'm an intellectual and I use lambda. So phi double prime is gonna be lambda squared e to the lambda t. I know, it's incredible. Then phi triple prime is just gonna be, you guessed it, lambda cubed e to the lambda t. And so on. I think the pattern here is pretty clear. I'm not gonna show it, demonstrate it. Like at that point, you might as well extend it to the gamma function, whatever it is. Honestly, it doesn't make sense. Anyway, so we've got these things, and again, we can just substitute them into this thing, our trial solutions, the thing that I refused to do at the beginning. But it makes sense here. It makes sense, I promise. So, in fact, it does make sense because if you substitute ln x into t, since that's what t is, into this thing, you just get x to lambda. The trial solution that I refused to do at the beginning, which would have made things faster, but also it would have been a shortcut. And I don't take shortcuts. I live on the edge, literally and figuratively. Anyway, yeah, that's easy to remember. So we can just write that down. Lambda cubed e to the lambda t minus 4 lambda squared e to the lambda t plus 4 lambda e to the lambda t minus e to the lambda t equals 0. Now, I don't think you need to know calculus to know that we can just factor out this e to the lambda t. So, e to the lambda t is just lambda cubed minus 4 lambda squared plus 4 lambda minus 1 equals 0. Alright, cool. So, this is what's known as the characteristic equation of this ODE, which is just a polynomial that we can solve pretty easily if you know your elementary algebra. And notice, because e to the lambda t is strictly non-zero, even if lambda is complex, it's non-zero, because that would break the logarithm, as you know. So we can safely assume that actually we can cancel that out, since it's not equal to 0, and we get this thing must be equal to 0. Now, time to find our first factor. And there's a couple ways to do this. If you're enough of an algebra whiz, you can just automatically factor this stuff out. I honestly, I think we're just gonna use the rational roots theorem, since here it's pretty trivial anyway. We can see that the leading coefficient is 1. The last coefficient, or the constant coefficient, is -1. What are the factors of those two? Well, just 1 and -1. So we may try one of those solutions, that set of solutions, and plug it in. That means just two things. So to see if it actually does equal to 0. So we get like 1 cubed minus 4, 1 squared plus 4 minus 1 minus 1. That's pretty unnecessary. You can see it's already 1 minus 4 plus 4. That gets cancelled out. That's equal to 0. Okay, so that holds. So cool. We've actually, yeah. Wait, hold on. I'm just gonna. Yeah, we've actually found our. We found our first root, namely that lambda is equal to 1, or better yet, that lambda minus 1 is equal to 0. Okay, epic, awesome, wacky and cool. Now, we're gonna, I mean, again, you could just factor this thing out of this, this equation by just splitting up these terms, but come on, man. Because I'm an absolute pleb, I'm gonna do pussy tactic, and I'm gonna use long division. Hell yeah, boys. So I'm gonna write it. Yeah, I'm gonna write it here. Just like that. It's not gonna take that one. So this thing's in my way. That's cool. All right, cool. I mean, okay. I'm not even gonna explain how to do this. You should absolutely know this. Like, why are you watching this otherwise? So lambda cubed, or lambda, or first, that's lambda squared. Lambda squared times lambda is lambda cubed. We want these two terms to cancel out when you add them up. But first, minus 1 times lambda squared is minus lambda squared. Now, times minus 1, this thing, so we can let this term drop down, 0. Now, this sign changes, so minus 3 lambda squared plus 4 lambda. Again, minus 3 lambda squared over lambda, it's minus 3 lambda. So, minus 3 lambda squared. Minus 1 times 3 lambda plus 3 lambda times minus 1, so 0, and plus lambda. So this term drops down, and hey, already we can see they're the same. So they just cancel out, pretty trivial. So lambda over lambda is plus 1, lambda minus 1 times plus 1 is minus 1, 0. Yeah, it's 0. Okay, it's done. We're done. We can stop. So what did we actually get from that? Well, nothing, except this thing. So that's cool. That's epic. That's epic and cool. So instead of this thing, we can now totally write. I'm just gonna. Plus 1 is equal to 0. Okay. Now this is a pretty, it's a quadratic, so that's already pretty easy to solve, to get the other two roots. Now, I mean, I really cannot be bothered to use quadratic formula. So what do chads do? Well, you just complete the square, really. It's quite simple. So, let's see. So we can just get lambda minus 3 divided by 2, 3 minus 3 over 2, squared, then 1 minus the square of this thing, so that's going to be minus 5 over 4, but we're going to take it to the other side, so it's plus 5 over 4. Now, so we get that the other two roots of lambda is 3 over 2 plus minus the square root of 5 over the square root of 4, which is 2. So, yeah, there's that, and you can also factor out the 1/2. I'll do that later. If you want, who cares? Alright. So, here, we've got all the 3 roots. Nice. 3, just as the fundamental theorem of algebra commands. Epic. Cool. Wacky. Kill me. Alright. So, we can say, we find a solution for our phi, so we can say that phi is equal to, now, the constants. It's doesn't matter. I can put them here or I can put them later, but just to be cool and epic and edgy. wacky and cool. So that's e to the 1/2, because remember what our original parameterization was. It was lambda. It was phi, lambda, not lambda. Fucking Greeks. Phi equals to e to the lambda t. So these were our roots. So plus, a nice linear combination going. 3 minus 5, square root of 5, plus c3 e to that. Don't forget the t's. I always forget, but you know. Alright, add them later, doesn't matter. E to the t, because one of our roots was 1 of lambda. So cool, this is a solution to phi, but that's not a solution to this thing. So we have to substitute back now. And that's easy, because to get our homogeneous solution now, all we have to do is substitute t with ln of x. And I mean, come on, what's e to the ln of x? Like, we just get c1 x to the 1/2, 3, square root of 5, no t anymore, that's gone. c2 x to the 1/2, 3 minus 5 plus c3 x. Nice! We're almost done. We're almost done, I promise you. But now just bear with me for one more moment, because now it's time to find this. And no, I will not be using variation of parameters. Please forgive me. It's really superfluous in this case. I really don't want to. And I mean, it doesn't make it harder. It really doesn't. It's just more work. So, because I found a way that's, again, doing the same things that I refused to do at the beginning, a trial solution, but that's how it goes with these things. So we can actually let our particular solution be of the form, because we have this thing here. So just as with a linear term, you would have ax plus b or some shit like that. Here we have just k over x. We can call it whatever. It's just some constant. Cool. All right. And it does work out. Trust me. I checked. Now again, same spiel. Differentiate this 3 times. Substitute. Bang. Solve. So y prime p is, again, the k is just a constant, so we're basically just taking the derivatives of 1 over x. So minus 1 minus k over x squared. Y double prime p is now positive 2k x cubed, and y triple prime p is multiplied by minus 3. In that, minus 6k over x to the 4th. Cool. So, substitution. And that's easy to remember, so we don't need that anymore. We don't need this either. No, and this we don't need either. So now substitution. So x cubed minus 6k over x to the 4th. And if you notice, this term is always one power less, one less than the power of this one down here. So it's always going to be in terms of 1 over x. So we're going to factor that out later. You'll see. It's quite a ride. 2k x cubed plus x. Running out of marker, goddamn. K over x squared minus k over x equal to 1 over x. Nice. Now we can just, again, we're just going to get 1 over x on each side, so we can just factor out 1 over x. Really simple. So minus 6k minus 2k minus k is equal to 1 over x. Look at that. As Dr. Payan would say, bang, bang, get out of this room, get out of this house, and we get that minus 10k is equal to 1, and such that k is equal to minus 1 over 10. Damn. Might have broken that. Yeah, boys. So we got our k. So essentially we're done, because our particular solution now is just, what was it? K over x, so minus 1 over 10x. Yep, that's that. So finally, it's time to get our general solution, y. So y is equal to c1, no e, x to the 1/2, 3 plus square root of 5 plus c2 x to the 1/2, 3 minus 5 minus square root of 5, whatever. My name Jeff, c3x minus 1 over 10x. We are done. We're absolutely done. We did it. It's over. Well, you didn't do shit. I did it. Man. Cool. And we can see that the solution is actually pretty underwhelming. Oh yeah, and by the way, funny story. Yeah, when I first tried to do this, I made a sign mistake, because of course I did, as every great mathematician does. And I'll just give you 3 options on what happened next. A, B, C. A, I realized my mistake almost immediately and I corrected it and never looked back. That's option A. Option B, I made a mistake, forgot about the mistake, and still got the right solution. However, I only realized afterwards I made a mistake, but it all worked out nicely in the end. That's option B. Option C, I spent an hour trying to use Cardano's method to solve an unsolvable cubic. I've been depressing the cubic for an hour before realizing I made that mistake. So yeah, that's option C. Pick your favorite in the comments. Who cares, man? Who cares? This wasn't worth it. Yeah, so see ya.
Do you guys remember Elliot Roger? He's basically a school shooter